All right, it's 1:15. Let's go ahead and get started. Thank you everyone for joining this session that's focused on time series variability features. My name is Eric Bellum. I'm the Alert Production Science Lead for Rubin. So just the usual reminders to start. There's a code of conduct for this workshop, so I expect everyone to abide by it and invite you to visit the code of conduct page if you have questions or need to report concern. This talk is being recorded, so if you don't want to be recorded, make sure to keep your camera and microphone off. You can issue questions and so on through Slack. There's a dedicated channel. There's also a set of notes that are being updated live by, thanks to Ian Sullivan for taking care of that. You'll see the video tomorrow if you wish. So the format for our session today is I'm going to give a brief introduction to the questions that the Rubin project is considering with regard to the selection of time series variability features. And then we have a number of representatives from the Rubin Science collaborations who have graciously volunteered to give some perspective from their needs. And this is, as you'll hear, the start of a longer conversation about how we identify the best set of features to use when the survey begins. All right, so let me dive right in and remind you that when we are surveying the sky, Rubin is going to be pre-computing time series features for kind of a variety of contexts. So we compute time series features, so summary statistics and so on difference image light curves. So during prompt processing, there'll be features that are included in the alerts and in the prompt products database for query on 12-month light curve history. And there also are difference image light curves in the data releases over the whole survey that will also have time series features. And also the direct image or object light curves that are produced in data release processing are also have features computed on them. So the sort of historic baseline we're working from is an allocation that's specified in the data products definition document, or DPDD, which is linked on this slide, that we have periodic and non-periodic features. There are 6 Rubin filters, and there are a total of 52 features that are allocated space. So those are sort of the numbers that we are working with in terms of sizing when we plan for database size and so on. And those baseline features, when they were chosen, were just taken sort of directly from the Joey Richards paper from 2011, breaking down, sort of into characterization of periodic variability with sort of a multi-harmonic fit, and then a variety of features capturing aperiodic variability, some simple summary statistics, moments, and so on. So there's a variety of reasons why it's a useful time to consider whether those features should be updated. In particular, that was sort of intended as a baseline choice, provisional, and since then there's been fully a decade of new work with a lot of progress on many additional surveys. And it's of course worth noting that a lot of the most state-of-the-art classifications these days are not even using features at all, but sort of deep learning architectures. There are also quite a few differences between the context in which the Richards et al. 2011 features were being computed and the LSST. The Richards paper was computing on single band light curves in the context of classifying variable stars. And while I'm sure there were, financial constraints and others that sort of limited in practice the number of features and computation time, there weren't strict requirements or anything on that. For Rubin, of course, we have inherently sparse multiband data. These features, I think, in practice are going to be used for a variety of purposes. They're not primarily for classification, but are also likely to be used in when folks construct filters for alerts, and also when they want to query the databases for specific types of objects. So they there's sort of a user-facing aspect to these features. And they also need to encapsulate the variability seen, not just for variable stars, but also transients, AGN, and solar system objects, as we'll hear from the various science collaborations in a few minutes. Finally, of course, just given the sheer scale of Rubin's survey, the number of features we store, we have to keep an eye on that. And for alert production specifically, we need to make sure our feature computation can fit in our 60-second latency window. So in terms of goals for the feature set we eventually work with, maybe let me start from the bottom here. Again, we want features that are of service to all of the major science pillars of the Rubin survey, everything from solar system and transient science, mapping the Milky Way, and of course the dark matter and dark energy mission. We need these features to be efficient. We want them to be broadly orthogonal, so there's not much purpose in recomputing features that capture essentially the same information as others. I think there's a lot of work we'll need to do in thinking about how to handle multiband data, especially as sparse as LSST's main survey. And I think I hope we'll hear from Eric Feigelson some of his thoughts on making sure that these are robust statistics and statistically well-founded. And finally, again, these are user-facing in a way that will, I don't think we can always be human interpretable, but I think to the degree that we can make it easy for users to reason about the features, I think that will make them more useful in practice. So I conducted over the last year and a half, slowed somewhat by COVID, a fairly extensive review of the time series literature, although I'm sure I missed some papers, and you're welcome obviously to message me and let me know, and I can add it in. This is Data Management Technical Note, or DMTN 118, which is again linked here in the slides, and we'll post after the session. So a review of many of the features and contexts in which people have been computing time series features, and sort of a listing of a range of practical concerns that emerged as I was sort of walking through this. And I don't intend to answer these questions right now, but I just want to lay out broadly some of them. One of them being, the DPDD assumes that there's sort of a single set of features used across the survey, but it's not obvious that that's the right choice. Maybe APN and the prompt real-time processing and the data releases should use different features. There's actually some complication and complexity around even which flux measurements we want to compute features on, whether those are the difference image flux or the total flux, and whether or not you're using the force photometry measurements that will exist. For solar system objects, of course, we know we need to address and to calculate the phase angle and correct for that, and we will do that as part of pre-processing before we compute time series features for known solar system objects. Obviously, you can't compute a multi-harmonic period from 3 data points, so I think there's some practical questions of at what points are we able to use various features, and how does that inform our selection of feature set? We expect the templates to change throughout the survey, and that will change baselines, especially for variable objects in AGN. And more broadly, how do we approach the question of evaluating the feature set we've chosen or that we're considering? So I've taken, mainly as a way of provoking reaction, I would say, taking the liberty of drafting sort of an initial feature set from the baseline, but smaller even. It's a Google Sheets document, which you can access through the link at the bottom of the screen. Broadly thinking of splitting the features in 4 major categories. One is sort of agnostic summary statistics like percentiles and so on. Periodicity related features, stochastic variability, and then transient characterization. So let me describe each of these in a little more detail. Again, for summary statistics, thinking in terms of just the raw per band flux percentiles, some fairly robust distribution features, and then Stenson J and K, normalized excess variance, and then a feature that would allow us to transform between templates, direct fluxes, and difference fluxes. For stochastic variables, I think we'll hear from the AGN science collaboration shortly. I think it would be useful to aim to provide something like damped random walk timescales and amplitudes, whether if we can do so efficiently. And again, especially in these summary statistics, as I think this Chico 2018 paper shows, we want to avoid really highly covariant features as much as we can. For periodicity, again, I think a baseline would be to look at the generalized Lumps-Gargle periodogram to provide as much as possible good estimates of the false alarm probabilities and some sense of the goodness of fit of the fold to light curve. I think this is an area where we'll really want to be able to do some, maybe not exhaustive, but some I think it's relatively straightforward for us to use model light curves with simulated LSST cadences to understand the practicalities of this in practice. For transients, again, I think computational time willing, I think it would be useful for us to aim to fit a parameterized model like that of Ashley Villar 2019 paper, which is also used in the Alerce classifier for ZTF. And so that's a kind of a generic functional form. If we're not able to make this work in practice, I think we'd fall back to some coarser estimates of peak and rise and fall slopes and so on. So the challenges in terms of how we get to a feature set, and this is part right, the reason this session exists is to move this discussion forward. There isn't any fully representative data set that exists today that really captures everything that LSST will have in terms of depth and color and cadence. And so we sort of have to use stopgaps even into commissioning, right? Because commissioning is not like the main survey in many ways, especially in cadence. So some combination of precursor data, simulations like the DP 0.2 desk DC2 or the plastics simulations, I think will have to be, those will all have to be tools in our toolbox. The other challenge is that the Rubin project, doesn't have an infinite amount of effort available to explore and validate sort of all the scientific corners that these features touch. And so that's where we're really hoping to lean some on the science collaborations to give us input and feedback and ideas. So I think, we'll be as expansive as we can, but absent that, I think I would imagine us aiming towards focusing on a smaller core feature set initially that we would have delivered and tested and understood by commissioning, and then look to think about enhancements in the data releases and alert production beyond that as the number of epochs increases and we understand it better. So obviously, the more we can get done up front, the more science we can enable. But I think we can also leave room for expansion and growth as we understand the survey and the camera more. So I think I've tried to emphasize here that we really need science user input and feedback here. And so there's a number of ways you can do that. You can send comments directly on the Google form. Even better, there's a discussion thread pinned on community.lsst.org. It already has quite a number of really useful replies dating back to June, and I think there's a lot more conversation to be had there. And finally, I hope that most of all that members of the Rubin Science collaborations will get together and think about how they can make sure that their science interests are captured in these features. And I hope that we're going to hear more about that in the next few minutes. So let me stop there and see if there are questions in Slack. Zach is there. I see, I'm looking on my phone now.
Yeah, it looks like we've got one.
Yeah, Josh is asking about interpretability. Are we thinking about an autoencoder based approach? I think the answer is it's not in the baseline. I think that's very interesting. I don't think right now that's something the project is prepared to build. But like many things, if there's a community developed if there's a community developed classifier or something like that that would be straightforward for us to incorporate in our processing, that's certainly possible. I think the challenge has always been that the project has been discouraged from saying that we're going to provide classification, but that we should aim to characterize and leave classification to the community. And so that's, I think, would be a little bit of a more gray area. So I think it also gets into questions of what is the project doing, what are brokers doing. Is that it's probably not a useful answer, but I think that's the best I can give you right now.
Yeah, I mean, it just from a computational perspective at we'll call it predict time, or at the time you need to compute these features, auto-encoded features will be much faster and could actually save you a lot of compute cycles than if you have to go through and compute all these summary statistics. And we and others have shown that when you then use those auto-encoded self-supervised features, you get as good or better classification than if you use the traditional statistical features. So it may, while it's not classification for the purpose of classification downstream, having those may actually be really useful for people. But again, you lose the interpretability.
Yeah. All right. Well, that's useful, and I think we've had this conversation at least once, maybe at SEMA back in June. But yeah, let's discuss this further. Francisco's asking, is it possible to compute some features on difference and some on total fluxes? Yes, I think that'll certainly be necessary, Francisco. It'll make it more confusing, but I don't see any way around it. Other questions I'm seeing in the PowerPoints to the alertSay features? Yes, that is an excellent document and features prominently in the review. All right, let me check. Richard Kessler's asking in the Zoom chat about robustness and simpler features. I would welcome your thoughts there, Richard, because I think you've got a lot more experience in this realm. These are real concerns.
Yeah, I noticed you fit to this general function, and you have this linear term, 1 plus sigma delta t. I've tried that too, and I'm just warning you, I've had robustness issues.
Sure.
When it works well, but it can also fail dramatically. So just be careful, and hopefully you guys can do a better job than what I did.
Maybe I'll see if, I don't know if Paula is willing to comment on that, since she's run it in production on ZTF, if she has any comments about how that's worked for you.
Sorry, can you repeat the question? I was disconnected.
That's all right. Richard Kessler was asking if there have been. He's saying that he's had robustness issues with linear terms in the transient models, and I was curious if you had seen that in your work at alertSay.
For the method we implemented, not, but of course you need a significant number of points to have robust results. Yeah, but with this modification that we did to the original model, we are obtaining very good results. But yeah, it's not a...
Is there a minimum number of points that you restrict to before you apply that fit?
Well, for the moment, we are using a minimum of 6, but I think for this model to work properly, at least 10 is something like that is needed. All because you have several, like around seven parameters. So.
Constantine asked, will the Rubin feature extractor be open sourced? Yes, all our code is open source. The main limitation right now is deciding on the features. So I mean, you can see the code that exists today, which is not the correct feature set. I think the broader question, which is somewhat unresolved, is whether our feature computation code can be easily extracted from the overall Rubin science pipelines, which is a much larger code base. That's not something we have to do, but I think it would be useful for many reasons. Stay tuned. All right, let's go ahead and move on to the next, the science collaboration talks. First is the AGN Science Collaboration with Gordon Richards.
Looks like I need to get you to allow screen sharing.
Yeah, I hope you'll be able to do it yourself. Gordon, are you able to share your screen?
No.
I'm surprised by that.
Should be in settings to the left of participants on your.
It says participant. Oh, I see. I need to check it. Okay. All right. Now you can. Sorry. Apologize.
Yep. No problem. Okay. Let's see. Can everybody see that okay?
Yes.
Okay. So there are a number of people in the AGN science collaboration that are mentioned in the DMTN 118 document. And the slides that I will show are coming from Demetri De Chico, Matthew Graham, and Wei-Zhang Yu. It's worth noting that I am not the Richards and Richards et al. 2011 and 2012, although those metrics are being used in the AGN data challenge that we are running for the next month or so. And I will drop a link to that in the chat when I get a chance. So this first slide is work from Demetri De Chico. It's a 6 in a series dedicated to optical variability studies of AGNs, making use of data from 1 square degree VST survey of the cosmos field. They have 54 visits in the R band over 3.3 years with an observing cadence of 3 days and a single visit depth of 24.6. So it's a useful proving ground for LSST performance forecasting. And then this next slide is De Chico et al. In preparation, where they present analysis of the structure function of VST Cosmos AGN, building a, sorry, I see that it's cutting off, so. I don't know. All right. Anyway, so they're basically doing analysis of structure function, building a sample of AGN confirmed by different means. The data set is opening up exploration of samples of sources that are about 2 magnitudes fainter than the literature to date. They find that the shape of the structure function doesn't change with sample depth while it is affected by the type of AGN included in the sample. And then the third slide here is from Matthew Graham. And so he says that we have theoretical models of AGN accretion disks, their structure and their dynamics. And we observe a variety of phenomena from them, from just burbling along to extreme events, some lasting days, some lasting years. And from this, we try to discriminate whether a source is an AGN, whether it's an outlier in the AGN population, and physical parameters that are imprinted on the variability, all to inform and refine our theoretical models. And then this sub-slide, analytically, what we want to figure out is the mapping from time-dependent data to physical parameters. So this time series analysis allows us to describe temporal processes as deterministic versus stochastic, as Eric was saying, or linear versus nonlinear. We can map out different types of behavior in astrophysical classes of objects to different regions of this space. And so the question is, where do AGN belong? We currently think of them as linear and stochastic, but that's not necessarily the case. One danger is that any stationary process can be represented by a linear stochastic model, like a autoregressive moving average. And we typically use the simplest form for AGNs, the so-called damped random walk, as Eric mentioned. And it assumes linearity, stationarity, and reversibility, but it's not clear that AGN actually have those properties. In fact, reversibility we know is not true. So, and then the next slide, the simplest solution is to just drop all of the assumptions and figure out the mapping from the input data to the output data. The theoretical basis of deep learning is such that this can be achieved by a neural network. These models can capture nonlinear behavior, which the ARMA models cannot. And advances are still required to handle irregular time sampling, the correct propagation estimation of errors, and general interpretability, but these are all active areas of research in the deep learning community. Okay, another solution to the damped random walk problem is to try higher order models, such as a Karma 2-1 model or a damped harmonic oscillator shown here, as compared to a damped random walk, which is a Karma 1-0 model. And you can see the difference in the PSDs as illustrated here. And basically, AGNs don't actually have a 1/f² structure function, and so this allows us, two more degrees of freedom in sort of characterizing the light curves. The terms on the right in blue characterize the perturbations, and the terms on the left in red characterize how the system responds to those perturbations. And then this slide here is showing how basically where AGNs are in this damped harmonic oscillator parameter space. So there's 4 free parameters in the model, this alpha-1 and alpha-2, and the beta-0 and beta-1, we're calling the ratio of those the perturbation timescale. And so you can see that AGNs map out a range of possibilities in that parameter space. And on the right, you can see what the light curves actually look like in those different parts of the parameter space. And then, we'd like to be able to make connections between what we are seeing in terms of the variability and actual AGN physics. So for example, a light curve like on the top might be a system whereby we're seeing the optical variability of the accretion disk. And then the next system in the middle might be a case where the X-ray corona is actually illuminating the accretion disk directly. And so you're imprinting the high timescale variability of the X-ray corona on the optical as well. And then in the last case, we have a QPO system, which might represent, say, a binary AGN. And so we are actually applying these models to real galaxies and stars and quasars, and you can see where they end up in parameter space. And one of the things to highlight here is problems in terms of aliasing, right? So the red box here are systems where it's trying to fit a cadence of 1 day or its harmonics, where we're having sort of time sampling problems, right? So I'll close by just saying, we're interested in sort of these more complicated parameters, karma models, and other sort of neural network type things. We sort of recognize that those take time to compute and may not be easy to produce as sort of a so-called level 2 data product. But the more things that are, the better. For example, the AGN community will certainly benefit from so-called level 3 data products from other science collaborations, and the ease to which we can share the information, more is obviously better. Okay, thanks.
Thanks, Gordon. I see a question from Paula in the Slack about exactly that question of runtime. Does a DHO fit in 60 seconds, or could it plausibly, or is there some approximation that is useful that would fit in 60 seconds?
Yeah, I mean, the actual DHO models that we're running, no, right? But is there like some sort of surrogate for that we could benefit from is an area that Weizhong, you and I are certainly looking into. And it may be that other machine learning models might be good enough, and we don't need to actually do a DHO.
Great. Any other questions for Gordon? All right, then next is Desk, represented by Gautam Narayan. Take it away, Gautam.
Hopefully you folks can see on the screen.
Yes.
Great. So Desk will not directly be using the time series features itself. Desk will be working with alert brokers to process the alert stream. This actually introduces an interesting issue in that we are affected by time series features, even though we're not using them directly, in two different ways. You can imagine that Desk scientists use the features to do some extra analysis that's not necessarily even strictly directly related to our early cosmology. For example, you might want to ask what the colors from sparse early time photometry are. For example, if you're interested in supernova, perhaps you're trying to identify an early blue excess to see if there are potentially different progenitor channels for type 1a supernova. And you might want to do this using some kind of non-parametric model fit for the transient. You might also want to know if, for example, a star or an AGN is exhibiting some really long-term change in behavior. And I don't think brokers will necessarily do that for the science collaborations. But there's also an indirect impact for time series variability features that can happen. Most of the brokers will run classification algorithms. Some of those algorithms, even if they are desk supplied, will use things like photoz's as inputs. And these are part, of course, of the alert features. And if those algorithms then start to report some object as a different class because of the input in the time series variability features, then those will ultimately affect our selection functions. And it can actually become more complicated than that. Desk is, for example, thinking of a feedback recommendation system. This is based off of Respect, which is a project between the Coin team led by Emily Ishida and Desk. And the idea is that we take the objects that we are most confused by, least certain about, and try to go follow them up, and then retrain classifiers over and over so that our classification performance improves over time. But of course, this assumes that the features itself that we're getting are relatively unbiased. And so this is also a really good way to bake in bias into a classifier going forward. So this means that Desk has to pay a lot of attention to these time series variability features for a bunch of our science cases. And I'll lay out the science cases here. So for things like early classification, if you want to do kilonova follow-up, or if you are interested in making sure that you get a spectrum of a supernova near peak, or identifying the progenitor, flash spectroscopy, all of those sort of things, then you really care about some kinds of time series features. If you are interested in, say, identifying strongly lensed transients, then you'll be very dependent very quickly upon the LSST data releases, because they will become the deepest optical infrared galaxy cluster catalog there is. And so will be where we identify most of these sources. If we are, for example, interested in, saying, finding Cepheids in other galaxies, then we will have a whole bunch of these observations of these objects to get the period luminosity color relationship. And it might be interesting to sort of see some of these stars actually become Cepheids, enter the instability strip during the course of the 10-year operations. People within Desk, despite the fact that they aren't typically used for cosmology, are interested in things like AGN. So for example, we heard from Chris Formeyer and the Foremost in Tides group about spectroscopic follow-up of these objects using Foremost to potentially do a higher Z Hubble diagram. You might also be interested in long-term changes in behavior to identify things like supernova remnants a few years after the explosion has faded. Maybe you can find a star that has high proper motion or unusual photometry as a result of being exposed to the supernova explosion. And we're also interested in, say, monitoring statistical properties of not just individual alerts, but the entire sample. And this is a useful proxy for the selection function as a whole, or to do things like anomaly detection. This sort of set of science cases informs what kind of features you want. And so I'll just change colors, and I'm actually going off of Eric's draft features that he put up on Google Sheets. So for a lot of things like early classification, you really care about things like having a photo-Z probability distribution function. And so Alex Miles, who's on this call, and I will be working on a letter of recommendation addressing Melissa Graham and Leanne's call for these photo-Z methods. And we're also interested in making sure that we have things like colors, assuming some kind of non-parametric model, as well as non-detection info for any alerts. If you care about identifying things like strongly lensed transients, then you want to make sure you have your alert association happen with more than just a simple cone search. And this, of course, actually came up in the alert broker section just before this, where if we're using some kind of fixed radius to do this association, we might miss a lot of these sources. It's a little bit more complicated than that. If you care about identifying things like Cepheid's Fourier features or some other way to get the total flux instead of just the difference flux matter. Carrying on. So the Dan walk features and things like to identify things like AGN sort of implies the requirement that we can calculate features on all previous force photometry. And that's a hard ask to do in 60 seconds, but I'd argue that the latency is less critical. And as long as this is done and goes out within even a day or something like that, it's probably more than enough. And monitoring statistical properties of a transient sample actually implies that we have some kind of access to an alerts database through the brokers or through the Rubin Science platform. This might be a use for this LinCC thing that one of the previous sessions talked about, so that science collaboration stand up little monitor services to actually keep looking at what they're doing. So I want to stress on a few of these requirements individually. So photo-Z PDFs in particular, point estimates we know from photo-Zs can be biased. And a lot of this early transient science, particularly at the higher Zs where we can push, will be impacted by photo-Z accuracy. So brokers and classifiers can effectively lose many interesting objects by simply ignoring them in favor of like low-hanging, easy to classify fruit. And there is some sense in doing that early science that way, but I'd say that the discovery space at high Z the volume is much larger, and so we shouldn't necessarily throw all of that away. And you can mitigate this problem by not reporting a single point estimate. So Alex Miles and company have shown that reporting quantiles does a much better job of preserving PDF information than simply reporting some kind of interpolated samples of experiments. And again, this may be computationally expensive, but I'd say that latency is actually less of an issue for all the science collaborations. And I will point again to this TVS survey that I hope gets rerun in the near future that showed that the input from a lot of the science collaborations was that we did not, in fact, need 60-second latency for alerts. And so I would say it makes a lot of sense to revisit that issue and determine if this is really a strict requirement for LSST users, or we can accept larger latency in return for richer data packets in the alerts. I recognize that Ashley is on this call and has done a lot of work on really great things like parametric functional forms, as well as people like Bazin and Karpenka, but none of them, I think, are as flexible as Gaussian processes or neural networks. And you heard this also, I think, from Josh's comment about autoencoders earlier. We're only calling these things non-parametric because they don't really include any physical parameters, but they are fundamentally parametric, and they're just never going to be as flexible as Gaussian processes or neural networks. The key has also been trying to make them interpretable, but I'd argue that something like sort2's color parameter is not interpretable in any case. So what we really are looking for is some way to get color at a phase. And that's what you really want from these fits. So if that's really what you want, it doesn't even matter if the classification is right. It's perfectly fine to use a non-parametric model like a Gaussian process or a neural network, even if it's non-interpretable, because of course, once you plot a light curve, it's totally interpretable irrespective of what the model is. And particularly if LSST cares about things like early classification for finding kilonova, we've shown, and this paper will be up on the archive tomorrow from Deep Chatterjee, that you can do it in the wide far steep, despite having sparse information, as long as you have a reasonable model that is conditioned on a whole bunch of objects that you expect to see with similar cadences. If on the other hand, you simply try to do a simple linear regression to predict the color, you'll do a much poorer job, and you have a much harder time of separating out kilonova from other classes. For things like associations.
One more minute, Gautam.
Yeah. I'll zip through this. So for things like association, it's just using something like the directional light radius as a baseline rather than a simple cone search radius. And that'll help you flag things that are in the vicinity of things like galaxy clusters, particularly you have a catalog there that you can associate with as well. And so particularly for strongly lensed supernova, that's going to be crucial. I hope that every time a template is changed, we also do reprocess all of the old force photometry and provide consistent fluxes with whatever the current template is. I think that'll be essential to make features interpretable, but also to find things that have shown pre-explosion variability, or to try to identify the progenitor systems of nearby transients. So for example, in this case, SN2012Z from Curtis McCulley. And finally, I'll say that there's this entire need to monitor for all of the science collaborations, entire populations of transients. And you can do that, I think, as part of brokers or as part of the Rubin Science platform. But the idea is that fundamentally, we can't do fake source injection in LSST easily, but we have so many transients that we can treat them as a statistical sample and monitor them itself to back up selection function is. This is also really useful for an anomaly detection. This is being done currently in real time on Antares. We're actually using this light curve package from Konstantin Mlanchev and encoding and using a UMAP encoding for the light curves to find transients. This is on actual ZTF data that's all on DNS. And all of those things on the previous legend were all things like supernovae, but you can see that that same filter already can pop out things like microlensing because they standard as an anomaly. I don't have time to get to this, but Eric's DMTN had a bunch of open questions, and I've sort of tried to take a stab at them basically as a summary slide from Desk's point of view. And I'll end there and take any questions.
Thanks so much, Gautam. Let's move on to the next speaker. But this was a great presentation, a lot for me to chew on, and I will certainly be going back and reading this more carefully. Our next speaker from the Informatics and Statistics collaboration is Eric Feigelson, kindly interrupting his vacation to join us. So Eric, take it away.
Hello, Eric. Thank you very much. Can you hear me?
Yes.
Okay, and I'll show some slides. There's only 6 slides here, so it's not very complex. There we go. Okay. So this is a cautionary tale. It's sort of a negative message, but I don't know how much of this sort of these cautions are really applicable, but I do think we have to keep them in mind for sure. And it could be that some of the things I'm saying are realistic. I don't really know. Simulations would be needed to assist. But the point that I'm going to make is that most time series features of all types will be statistically unreliable for general use, maybe not for specific uses, at the early stages of the LSST mission, particularly for the wide fast deep survey. So my assumption is that there's the WFD will have more or less the universal cadence of 80 to 100 visits per year to a given object, but it'll be rotating through 6 bands. Now that's very important. If it's only rotating through 2 bands, things are much better. Okay, so this means that instead of 80 visits per year in a given band, you have only 12 or 16 or something like that. And they won't be evenly spaced. There's various cadence patterns that are being widely discussed, and they'll be combining the WFD with the DDFs and the mini surveys and other things as well. So I'm sort of more concerned about the first year, maybe the first couple of years, than I am about the 5 and 10 year mission when things get really denser. Okay, the DDF cadences are obviously going to be denser, but from my reading of the situation is that they're still very complex and not regular in any way. So here's just a little bit of simulations. Okay, this is just Gaussian random noise. Okay, if you have 5 points, let's just say 10 points here of Gaussian random noise, 40% of the time, the means are sorry, half of the time the means are inaccurate by half a sigma. Okay, so the means flop around by half a sigma for small n, and then of course it becomes Gaussian and it converges. The medians are sort of worse than that for Gaussian noise. Okay, The standard deviations are similarly bad, and the MADs are even worse. But it's not obvious this means that we should use means instead of medians, because this simulation assumes Gaussian noise. If it's a non-Gaussian system, then the situation is likely to be reversed, and the non-parametric medians and MADs are going to be better than the means and standard deviations, which are standard deviations in particular are very sensitive to outliers and non-Gaussianity, notoriously so. Okay, and so this is optimistic over here. It can't get any better than that. The good news is that we can test for normality, for Gaussianity, and we should all the time. The Shapiro-Wilk or the Anderson-Darling tests. That's not a time-dependent test. You just take all the fluxes and just do a histogram and do a non-parametric test, an unbinned test. So there should be tests for normality built in to time series testing. There's a lot of interest, of course, in periodic sources of all types, and people use the Lomsdorff periodogram, which is a generalized Fourier transform, and it is a good periodogram. It's actually derivable from fundamental Bayesian inference with simple priors. And I think for high amplitude variations, sinusoidal variations, such as Cepheid's, okay, it should work with small n, because the Hubble Space Telescope Cepheid program works with very small n's that are cleverly spaced. But as soon as you get non-sinusoidal variations, let's say eclipsing binaries or something, or low amplitude, let's say rotating star spots, the small n really can't be assumed that you'll get highly informative periodograms. And then, of course, comes the question, which Eric mentioned, of false alarm rates. And you should note that there's a great deal of debate for 20 years on FAPs, false alarm probabilities, for Lomsdorff periodograms. And the situation is not very good, okay? There's a paper that people don't remember from Chris Cohen, who, by the way, has a PhD in statistics, that even this issue of not knowing the population variance and only the sample variance is enough to screw up all the FAPs. I mean, just that problem alone really is devastating. No less all the other debates. And this particular footnote is a list of the papers that concentrate on a particular approach to the false alarm involving the generalized extreme value distribution, which I think is quite interesting. And so there is some optimism. But if you actually read these papers, you will see that there is no consensus. Okay, the idea that Zechmeister and sort of solved this is wrong. Okay, there is no consensus. And B, if you want to choose one of the more advanced methods, let's say Sulis or something, or Dalil, it's very complicated. It's not simple at all. And there's no reason to believe that these calculations are going to work when the original sample has 20 objects, 20 measurements. And similarly, you can't get a correlation, an autocorrelation function, for instance, the Edelson-Krolik autocorrelation function, if it's too sparse, which is another way of saying that you can't really fit ARMA models in an objective sense. Now, you can assume AR1, which is CAR1 or AR1, you can assume it and get a coefficient, but it's not clear it's sort of a valid model in the classic sense of time series analysis, where modeling is then validated using statistical tests. So I want you to know periodicity with small n and non-Gaussian behavior is a huge problem. I mean, it basically can't be done by any method. Okay, that's the argument I'm making. So TVS and I am leading a small group of TVS and ISSC scientists to do something. It's not going to solve the problems, but at least it's an interesting, different approach. And that is just to look at a single field on a single night in a single band to get over 1,000 regularly spaced observations every 30 seconds for about 1 million objects, whatever's in one field. Most of them we concentrate on stars. And then with that kind of data set, 1,000 data points evenly spaced, approximately evenly spaced, then you can do tests for normality, tests for autocorrelation, tests for trends, ARIMA type modeling that doesn't make sort of strict assumption. You can do Fourier analysis for that, Norm-Scargill, and you can do wavelet analysis, change point analysis, and basically dozens and dozens and books and books and books and codes and codes and codes of already written codes, all in MATLAB and R, not all in Python, are all available to you if you have 1,000 evenly spaced points. So we propose that maybe one night of commissioning be spent in this way. And we would then use that to try to help understanding the time series features that Eric's document is going to arrive, and try to connect this excellent data with this weaker data that we're going to get from the WFD service. So that is my entire presentation. Time series features will be uncertain, and forget about 3 sigma tests, which are tails of distributions. I mean, you'll just forget about it for years. Okay, you don't have enough data to know what's going on the tails of your distributions. I mean, you can arithmetically calculate it, but they're not stable. Okay, so characterization classification should improve with the later years, but will be very sort of wobbly. Okay, now stationarity, by the way, has to be assumed. Okay, that means you have consistent behavior throughout the observation. I think that quasars and CVs and Cepheids, there's certain high amplitude stationary sources out there, which I think we will be able to classify them reasonably well. Maybe not the broker level, but in 100 days or 300 days or something like this. And also when you have something that you can use a match filter on, for instance, a supernova rise and fall, a stellar flare with what's nicknamed a FRED, fast rise exponential decay, or asteroid motions. When you know something and you have a parametric model, everything improves, and that definitely helps things a lot. Okay. Autocorrelated and periodic behaviors will be difficult to characterize, except, that's a repeat, okay, and false alarm periodograms are bad at the beginning. And this kind of testing will help a bit. It will actually be very informative by itself. You'll learn a lot from one night, one band, one field. But it should help understanding the WFD as well to some degree. So I'm sorry to give an unhappy report. And it may not be a consensus by all statisticians, but I do read a lot of statistics, and this is my view.
Thanks, Eric. Appreciate that bracing and informative talk. I feel somewhat less concerned, mainly because that maybe relieves some of the pressure on the early survey in terms of the time series features. But there's a question from Tom Laredo in the chat. Are the tests for normality that account for measurement errors similar for stationarity, et cetera?
Generally not. If the measurement errors are homoscedastic, the answer is yes. It doesn't matter. Homoscedastic means the dawn, the midnight, and the twilight are the same. But if you have a lot of heteroscedasticity for some reason, then those will be biased and not as effective. I still think you should run them, but they're perfectly fine for homoscedastic data.
Great. All right, let's move on to the Solar System Science Collaboration. Bryce Bolin.
Okay, I'm going to share screen now. Okay, can you see my screen?
Yes.
Okay. All right, so I'm going to talk about the variability is seen from the solar system perspective. That is the variability of objects that are detected in Rubin Observatory, which are asteroids and comets. So first, before I get into that, I'll discuss a bit about the orbital elements, because this is relevant to the discussion of variability. So namely, there are two main orbital elements that are important in the discussion of variability. all of them are important really, but the two main ones I want to focus on are the semi-major axis, which is half the width of the ellipse that describes the orbit of an object along the long axis, as well as the eccentricity, which is the extent to which the ellipse is elongated, where 0 is a perpendicular circular ellipse, and E is starting to approach more like that of a straight line. And then we have two other quantities that are based off of these. One is the perihelion distance, which is lowercase q, which is the shortest distance that the object is relative to the sun, where the sun is one of the foci of the ellipse. And the aphelion, which is the maximum heliocentric distance, which is denoted as capital Q. So when we're talking about variability, that the brightness, you have brightness changes in the, of solar system objects due to their evolutions in viewing geometry, which comes from their orbit. So I mentioned before that we have the different components, lowercase q for perihelion, uppercase q for aphelion. However, these describe the bounds of which an object can range in heliocentric distance as well as geocentric distance. So for lowercase r, where that is the vector that is pointing from the sun, the heliocentric vector, that is described by lowercase r, and that has a value between q, lowercase q, and uppercase q. And then we have the value of delta, which is the geocentric distance, which can range for a given line of sight vector pointing towards the direction of an object, can range between delta lowercase q and delta uppercase q. That is the minimum and maximum delta that object can be along that line of sight. Then there is a third quantity called alpha, which is the phase angle. Sorry, I forgot to have the captions here. And alpha is the phase angle, which is defined as the angle between the sun and the observer as viewed from the asteroid. And this can range in values greater than 0 degrees and can be fairly large, up to 9 degrees or more. So how does all this describe the brightness of an object? So this is the modified Boole HG phase function, which describes the apparent brightness of an object as defined by several terms. So the first term here, capital A, V is let's call it the apparent magnitude. H here is the absolute magnitude. It is defined for the unphysical quantity where an object is at 1 astronomical unit distance from the sun, 1 astronomical unit distance from the Earth, and at a phase angle of 90 degrees. But this is just something standardized. This is what we use to define the absolute magnitude. The next term is the distance component, which is comprised of the heliocentric distance and geocentric distance. And then we have the phase component, which is comprised of the phase coefficient, capital G, and basis functions phi sub 1 and phi sub 2, which are then themselves functions of alpha, the phase angle. And G is a property that can vary depending on taxonomic class, but it has a typical value between 0.5 and 0.3. And then this last term, lowercase delta, is periodic variability term due to the rotation and shape of the asteroid, which is typically between 0.2 and half the magnitude in amplitude. So what does this look like as an object is evolving in position around the sun due to its orbital motion? It can cause variability that can be quite drastic in its apparent brightness. So these are for close approaching asteroids that come within several lunar distances. And the relative size, the relative change in distance in the delta component can be quite large, which can give them a very large change in magnitude, up to more than 3 changes in magnitude. So this is for close approaching asteroids. However, for more distant asteroids, the variability over the course of a year can be in the range of 1 to 2 magnitudes. This is just purely from evolution in the viewing geometry. Now, when you remove the distance components, the 5 log R delta component, you get what is something called phase curves. You can get the brightness of an asteroid as a function of its solar phase angle. And so at 0, you're at full illumination, and you have something called the opposition effect. And that's why you see in these curves, you see kind of a peak around 0. But in general, if you take targeted observations, a dense coverage of these phase curves, where you're observing an asteroid at phase angles 0 through 30 degrees, less than 30 degrees, you get this nice curve here, and where in general asteroids gradually brighten as they get closer to a phase angle of 0 degrees, and they drastically brighten at around less than 1 or 2 degrees. And these can be densely sampled for targeted observations of specific asteroids and specific dates. However, in surveys, and such in the case of Rubin Observatory, LSST, you will have sparse coverage. You will have basically serendipitous coverage, where you will be observing asteroids sparsely along their phase curve, along their phase angle. And this is a simulated example of that for a given asteroid made by Mario Jurek and Siegfried Eagle. That's what a typical phase curve will look like in LSST times for a given asteroid. So now we're going to talk about rotational variability.
One more minute, Bryce.
I'm sorry?
One more minute.
Oh, okay. Sorry about that. So as the asteroid rotates, its viewing cross-section can change due to its shape. And this can cause periodic variations on where the period corresponds to its rotation period. This can be seen in dense light curves, such in the case of targeting one specific asteroid, such as the case for interstellar object 1I, where you have large amplitude variations. You can also have very, very small amplitude variations, which are less than 0.1 magnitude. But in LSST times, you'll have something that's more sparsely sampled, but with advanced techniques, you can actually reconstruct the rotation phase of an asteroid, where you observe an asteroid every few days. Now, the last bit of variability comes from outbursts, a different kind. It's not due to rotational variability, but it's actually due to some kind of special event outburst in the asteroid. As this case was seen for asteroid Galt by CTF, where it had an outburst of more than 2 magnitudes, where following that 60 days later, you had a stellar appearance, but then about 60 days later, you had the growth of a tail. So what you had is you had an outburst of dust, and it took 60 days for that dust to become resolved as a tail. But this is kind of a special case. So here are the conclusions. Brightness variability can come from secular changes due to orbital motion, as well, which is comprised of distance changes in distance, phase angle, and is more drastic for close-up objects. Then you have phase curve variability due to the phase effect, where brightness changes with phase angle. And you have short-term variability due to the rotation of the asteroid, typically on the time scale of hours. And then you can have as well abrupt changes due to a spontaneous outburst due to various sublimitation volatiles and rotation and disruption events. And this can actually be a way to detect these and predict these outcomes, where you have an outburst occur where the brightness increases in this light curve, and you have the following extended evolution of an extended appearance.
Thanks, Bryce. We are at the end of the normal session. We've still got, I think, a couple more science collaborations to talk. Obviously, if you need to drop off for some reason, you're welcome to. But let's continue with the TVS. Konstantin, do you have slides?
Yeah, hello. Can you see my slide?
Yep, great.
Right. So hello, my name is Kostya Malanshev, and I'm presenting time series view from the point of transient and variable star science collaboration. So transients and variable star science collaboration covers a lot of aspects of variable sky, not only transients and variable stars, but also Microlensing events, for example, or tidal disruption events. So it covers all variable stars, things from our galaxy to extragalactic things. And of course, I couldn't cover all the cases in the short talk, but obviously light curve features could be used for 3 large tasks. One is classification of objects to several types. Second is hertzization. The good example is a period extraction, which is obviously a good physical measure a characteristic of the object, and anomaly and node detection. So as I said, I will highlight only a few feature possibilities and only a few features mentioned in the document we discussed today. So first thing is to support the thing that Eric has already said about parametric feeds. So for fast rise, exponential decay transients like supernovae or kilonovae or something like these objects, parametric feed could be done. We could use Bayesian function or any other function which is good here. Of course, it is not so good for alert science, because if you can fit decay, you probably have already missed the object. But it could be used in data release features to find some missed transient or to find some transient which could recur. So the example here is from early ZTF survey. Here's alert photometry, which few points only, and here very a lot of observations from Detroit's photometry, and you see good Bayesian function feed. And we can use, if the store doesn't allow us to keep all parameters, we can use goodness of fit only, for example, and it would be enough to find such objects, for example, data release or in a live stream. So other thing which I haven't found any mention in the document is flaring variable stars or apposite eclipsing stars. We could find a way to split the light curve to plateau part and outburst part, outlier part, and to extract some features from these two groups. For example, ratio of observation count, difference of means of these two groups, or variance in each group. Here, the example for dwarf novae light curves from Ogle. Next, I would skip it because multiband periodogram was described well by Eric in the first talk. But I would mention that non-parametric multi-passband periodogram can be useful too, and probably we could consider such opportunity. Maybe it would work better than multi-passband Lamb-Spangle. Not sure, but this paper showed this. Next, I would highlight non-detection features. I know that they are mentioned in the document, but it is worth to highlight it because Aller's papers show that they are really useful for transient detection, at least these three highlighted features. And we probably should have some non-detection features in alert packages as well. And the final slide is about really different way to extract features, namely DMDT maps. They have been used for classification and for anomaly detection. And this is some kind of transform of your light curve to a delta magnitude, delta time space. And each light curve has some unique pattern in this space in such map. And we can use low resolution DMDT maps, which are very good, which contains integer numbers only. So they are small, we could use short integers, and they are really good compressible. So we can compress it by the factor of 2. So data storage probably is not a limiting factor here. That's all. Thank you for your attention.
Excellent. Thank you, Kasia. Let's see, did someone from the Strong Lensing Science Collaboration join? It wasn't totally clear we were going to get them or not. All right, then I think we will check and see if there are questions that didn't get captured. There was lots of good Slack discussion. I think we got most of these. think we've got most of these captured in the Slack discussion. Any last questions anyone wants to raise by raising a hand? All right, well then, thank you everyone for joining this session. We'll close for today. See you tomorrow for another day of PCW. Thanks so much, everyone. Bye all.